Welcome to today's webinar on additive manufacturing. And today we're going to be looking at, in particular, fatigue of additive manufactured components and materials. So I'm going to start off by going through an introduction, just about what additive manufacturing is. Then we'll have a look at the tensile testing and tensile properties of typical materials. Then get on to the bit really that we're interested in, which is fatigue testing. And then I'll go and conclude with some conclusions of what we've done and to look at further work that we're busy undertaking. So why are we worried about additive manufactured materials and components? Well, according to the British government survey, then around about $5.3 billion is the value of additive manufacturing business sector in 2015. And we see from that plot on the side there that the government's own figures show an exponential growth. So clearly there's a lot of interest in additive manufacturing. Why are we particularly interested in it from a fatigue perspective? Well, a very recent report in 2015 from Lloyd's Register, the insurance companies, was showing that their #1 focus recommendation was for the safety of systems containing 3D and 4D additive manufactured parts. And for those who are wondering what 4D are, these are components where we print them in 3D with the idea that there's either residual stresses printed into them so that when we release them, then they can change their shape. So we're manufacturing into them residual stresses, essentially. That report goes on to say that fatigue is a principal failure mode of structural additive manufactured components, and it's a hurdle to its general acceptance. And that's really where nCode comes in and why we're so interested in it, to find out if we can tackle that problem and make additive manufactured components safer and more reliable to use. What additive manufacturing gives us is really a big increase in design freedom. It reduces the need for machining, and we can make components the sort that we couldn't do before in an economical way, because we only use the materials we need. We don't have to effectively mill them away from a solid block anymore. Over the last 12 months, my colleagues and I have attended several additive manufacturing seminars, and pretty much all of them have concentrated almost exclusively on topology optimization. And today, just if we did a quick check on Google, you'll see that there is a huge number of companies who are dealing with additive manufacturing from this idea of optimizing. But it's not all about shape. It's the material strength, and in particular, the fatigue performance, which is crucial. Going back, this is again from Lloyd's Register here, and this is just one example of a guidance note when it comes to certifying and qualifying additive manufactured components. It says, additive manufacturing techniques have significant barriers to overcome in delivering a manufacturing process that produces consistent quality and safety. And that's really what we're trying to tackle here. It concludes by saying, the acceptance criteria specified shall consider all reasonable foreseeable load cases. For example, if the part is subject to dynamic loading, the fatigue performance shall be specified with an acceptance criteria. And it's finding out about how these materials behave in fatigue and how they're different from wrought materials. Of course, this hasn't stopped us as an industry using these wonderful new materials and these new manufacturing techniques. Here's just a few slides showing how they're used in different engineering sectors. So, for example, the oil and gas, offshore oil and gas, this was a new additively manufactured part which was certified by Lloyd's Register. It's a titanium gateway manifold used for pipelines. Of course, it's not just the heavy industries, we've also got aerospace. In 2017, just last year, the first production component was put into by Airbus into their production aircraft, a 3D printed bracket on the A350. And obviously, Boeing is not to be left behind, because last year they also approved their first 3D printed structural titanium components. There are other ways, as well as additive manufacturing, that we can start to build components. And one of the key things is powder metal, which is one of the components of additive manufacturing, really. Powder metal itself allows us to create net-shaped components, particularly by hot isostatic pressing. And again, here's an article showing how powder metallurgy was used to produce these engine components. Let's not forget that this isn't all new. The very first patented hip implant was done in 2014. And again, in the biomedical industry, fatigue is just as important as in aircraft and offshore engineering too. So it's clear that additive manufactured components are actually very popular. And we need to discover more about how we can use them to make sure that we can use them in our structural components. So what's the objective of this presentation then? Well, primarily it's to show that fatigue testing is important when it comes to designing additive manufactured components. Secondarily, it's to obtain mechanical properties of a material, in inverted commas, that we can use in design and analysis. So I have to admit that when we started doing this work over 12 months ago, we'd had some involvement in additive manufacturing in fatigue, and up till that point, we'd not really found any materials that we've been given that have got acceptable fatigue performance at all. But starting really last year, we found then that we were getting components coming in which did show credible fatigue resistance. The key thing here is what constitutes a material. So in the test that I'm talking about, when we look at materials in inverted commas, we're considering the holistic material. We're implicitly accounting for the raw material, the manufacturing methods that's been used, any machining that's been done afterwards to create the specimens, heat treatments, surface treatments, any fabrication, joints and welds. These are all considered to be implicit in the components that we're testing right now. We're not looking at trying to model those separately. The purpose of this presentation isn't to try and promote one manufacturing method over another one. You have to realize that when we're doing things, fatigue performance of a material or of a component is just one of its acceptance criteria. There are many other criteria, and different techniques offer different advantages and disadvantages. So we're not trying to recommend one process over another. We're just trying to assess how fatigue is affected and how useful components can be from a fatigue perspective. This presentation today, I'm concentrating on one material in particular. It's a titanium alloy, Ti64. It's a wonderful material. It's high strength, high stiffness to weight ratio. It's got excellent corrosion resistance. And it's used in all industries, aerospace, automotive, oil and gas, biomedical, and so on. It's one of the most commonly used titanium alloys. The reason that this is particularly well suited to additive manufacturing is it's notoriously difficult to machine. So the fact we can use this wonderful material through additive manufacturing means that it's got a lease of life really from that, because machining it ordinarily was awkward. What we're going to do is we're going to compare the tensile and fatigue test results, and we're going to look at different manufacturing processes with the same material. So we're going to start off with wrought bar and rolled sheet as our sort of background level, so we can see, we can assess additive manufacturing powder metal in comparison to those. We're then going to look at powder metallurgy, hot isostatic pressing as a method, and look at how that compares to the wrought bars. And then we're going to look at two methods of additive layer manufacturing using powder bed fusion. In particular, we're going to look at selective laser melting and also look at electron beam melting. So the method then that we're using here is, first of all, when it comes to powder metallurgy, then what we've got here is a partner of ours has given us components which they've made using powder metallurgy and hot isostatic pressing. This really, I suppose, is a replacement or a new way or an alternative way of doing the type of casting things. We can fill a cast, if you like, with powder metal, and then through hot isostatic pressing, we can actually create a component like the ones that we saw earlier. These go into a furnace. The pressures are typically 100 to 200 megapascals at temperatures between 900 and 1250 degrees C. The idea of this is it provides isostatic 100% densification. So it squashes those, heats them together and fuses them together to make a material and a component. The other thing we're looking at is powder bed fusion. So this is where we use selective heating. So typically, a little illustration here of a typical process. We have powder delivery system. This takes the powder from a thing and it lays a thin layer, and then we use a laser or some form of heat to locally heat it and to create the component. And we're looking at two different scanners here, selective laser melting and electron beam melting. Now, in addition to those, we can do post-heat treatments as well. So we can create an additive manufactured component using powder bed fusion, and then we can heat treat it by hipping afterwards. And this has the effect of homogenizing the properties somewhat, so they become far more consistent, and in our case, better potentially in fatigue. So we're also looking at different combinations of hipped or unhipped processes. So first of all, let's have a look at the tensile properties when we do these sorts of tests. Electron beam melting, first of all, appears to have the highest yield and UTS values. If we look at these plots below, what this is showing us is in the red square, we see tensile tests which have been cyclically stabilized before testing. So we've taken a tensile specimen and we've applied some, if you like, fatigue cycles, usually a couple of hundred cycles to it beforehand. That enables us to get shakedown, and then we do the test. The ones outside, to the left of that red box, these are the traditional monotonic tensile tests. We put a coupon in the machine and we pull it and we do the tensile test. And what we can see here is the different UTS values for either bar, sheet, or we've got powder metal hip process there, selective laser melting, and electron beam melting. The first thing that you notice is that we have quite a bit of scatter on the sheet when it's in the monotonic test. And that's really the reason why we do cyclically stabilized tests in this case. The sheet and the rolling process can induce residual stresses, and that can give us scatter. By doing that cyclically stabilized test, it reduces that amount of scatter somewhat. So the interesting thing here is that when we look at those tensile properties in UTS, there's no real difference between the powder metal and the additive manufactured from the wrought materials. We can also compare what happens with the yield strength as well. And again, we notice that there isn't really a big difference. Yes, the electron beam melting's got the highest yield, but really they're all within the same sort of ballpark as the bar and the sheet. And going further, if we go beyond tests that we've done in our labs, then I can show you here some tests that have been done in a publication. So you can find this on the internet or in a paper. And again, this one shows us the different sort of expected tensile properties across a whole range of different of the same material under different conditions. And we see that what we're finding here is consistent results. So when it comes to tensile properties, then the additive manufacturing are pretty much in the ballpark of what we expect from the wrought materials. Tensile properties don't seem to be affected significantly. So how about the fatigue tests then? Well, for the fatigue tests, we've used several different geometries. We've first of all taken as our background wrought material, we've got 65mm bar stock material, and we've also got sheet material as well. So these allow us to create, if you like, a background of what a wrought material fatigue property curve would look like. And then in addition to that, we've used powder metal hip processing, so 14mm square section blocks for that, and selected laser melting, a 13mm bar. And we can see here the gauge section and the specification that we've got for those fatigue specimens. All the tests have been done at room temperature up to yet. They've all been done under strain control using a sinusoidal waveform, and they're fully reverse tests, so equal compression and tension. And our failure criterion has been to look for a 20% load drop. So first of all, let's have a look at the fatigue tests from the standard bar stock and sheets. So these are wrought materials and rolled sheets that we've got in our existing database that we've tested in the past. There's 65 samples in total. They're taken from 3 different batches. One batch of sheet and 2 different batches from 2 different manufacturers of 65 mil bar. And we can see here we've got those points, we've got a regression line through them, and I've also drawn the 3 sigma, the plus or minus 3 sigma deviation lines on there. And what we can do is we can use this as a background to overlay our additive manufacturing as a way of reference to see how much it changes. So first of all, let's have a look at the electron beam melting. So far, we've tested 15 samples. We've actually tested quite a few more than that now. But the 15 I'm putting here have all been tested with a HIP post-treatment with them. And the first thing we notice is that they've got a very low scatter. They hug the curve very nicely. And that's a very good indication of the quality of the material. If you find that there's lots of porosity in materials, it tends to have a lot of scatter away from that regression line. And the first thing we notice here is that's not happening. It's hugging the line quite nicely, and that means that we're getting good quality and consistency in what we're doing. You will notice that the lives are lower than the stock test that we're comparing them with, but they're not that much lower. They're within a sort of 3 sigma. The other thing that you notice is the slope, the B slope of the curve is slightly steeper. And again, this is what we'd expect. So what we find is that at the low cycle fatigue end, then they're tending to be similar material to the standard stock, in the same way as the tensile properties are similar. But at the high cycle fatigue end, we're seeing that the fatigue performance is not as good. And that's exactly what we would expect from these, because at the high cycle end, then surface imperfections, porosity, irregularities become far more dominant. At the low cycle end, the load is the most important thing. But at the high cycle fatigue, it's all of the little things like surface effects, like porosity, which become increasingly more important. And so this is exactly what I'd expect. However, the nice thing is that HIP post-treatment has actually brought the fatigue properties to within really a realistic level. They're very usable at this. Now this test considers powder metal hipped. So there are 25 samples here. The first thing we notice is there's more significant scatter. It's not bad. It's in the order of the wrought material, but there's a little bit more scatter than we found before. But still, the life is within that 3 sigma band. And in this case, there's no real significant change in the B slope either. Now, right now, to date, we've only got 2 samples using selective laser melting. And these are below that 3 sigma level here. Now, partly that's why we've only tested 2 levels, and partly this is because these are not hipped yet. So the idea was to try and find a base parameter so that we can look at hipping. And it's not just one type, but several types of hipping and post-treatment to see which ones are likely to give us better results. So right now, the results aren't bad, but we only have those 2. So that's something we're going to concentrate on in the next few months. So in conclusion then, when we look at fatigue tests, then I think you'll agree that even with hipping and things like that, additive manufactured components and COOP materials generally have a lower life than the original stock material. However, that modern HIP processing can generally bring the life to within 3 sigma, and that means that it becomes practical for real structural applications. Material testing and characterization are really essential when you're looking at both powder metal and additive manufactured processing. You can't just use the fatigue properties of the wrought stock data. You've got to go and measure them, and that has to really include the process that you're using, the manufacturing process and the heat treatment process afterwards. But one of the really nice things to come out of this is that it's proving that we can use ordinary strain life methods in the case of this TI-64 to predict the fatigue of additive manufactured components. And that's something new. That's something that we didn't necessarily expect at the beginning. At the beginning of this, we went into the analysis thinking that there was probably 3 cases. The best case would be that we could use EN or SN techniques. But failing that, we'd look at initiation from porosity and imperfections as being an approach. And if that didn't work, we'd probably look at using an approach based on composites type analysis, where we treated it as a composite material. But from this, we find that that hipping and those heat treatment processes at the end are making it far more homogeneous as a material, where we can use isotropic properties, and in this case, use a nice strain life approach and treat it pretty much as any other material, albeit the curve is different. So what have we got left to do then? So right now, we've done the strain life fatigue testing on base materials. We've also looked at powder metal with a HIP processing, and that's shown to work very well. We've considered electron beam melting, and we've looked at selected laser melting, but we've still got more work to do on that because at the moment we've only got those 2 samples that we've tested. We're also working with the university here on an EPSRC grant. This is looking at wire arc additive manufacturing. So it's almost like, if you think about it, it's almost like making components out of weld metal. So these are much larger scale components that we can do here with some interesting heat treatment techniques. We also want to look at some component validation. Now, technically, a specimen that we're doing, an hourglass specimen, is a component when it comes to additive manufacturing because we have to print that component, but we know that we also do a lot of machining too, and we also want to look at how much we can read across from real small components which have been printed. So right now we're looking at getting component validation using the same base material. Now, in addition to that, there's other important things that we know we need to look at. The first one is build orientation. So right now, all of our specimens have been printed in the A direction. So essentially, they're cylinders which are vertical, and we build them up layer by layer in that plane. Now, we also need to consider what happens if we build them up in different angles and how that performance changes. So is it going to be that they have a strong and a weak direction from doing that? And if they do have a weak and a strong direction, is it sensible just to always assume the weakest curve and design for on that basis? In order to do that, we need to understand what degree of scatter there is in those curves, and also how that's affected by those heat treatments, because certainly our initial look-sees seem to be claiming that the heat treatments afterwards, the HIP treatments, are helping us to sort of homogenize these materials so we don't get this orientation effect. But this is something that we really do need to research more fully. Now, we do know as an industry already that we take care of, when we've got areas of high stress, then we very often orientate the printing of the components to make sure we have a favorable layup when we've got those high stressed areas. But again, what I'd like to do is to just be able to quantify those effects to see how we need to model them. Of course, going back, the worst case scenario in terms of modeling is that we treat everything as a composite, which has non-isotropic properties, so different properties in each direction. We've still not ruled that out, but so far the results are looking quite favorable. The other thing that we want to look at is surface finish as well. So we know that fatigue cracks initiate at a free surface. And the thing that we've tested right now is we printed bars and then we've machined the bars into typical fatigue coupons. What happens if we were to print the coupons themselves? So in many cases, when we're looking at additive manufactured components, we're printing surfaces and we can't always get to polish those surfaces, and we know that fatigue initiates at those surfaces. So what can we do to estimate the effective surface finishes? So we're looking here at basically as printed net section shapes for testing. How do they all compare? And when we've got a structurally optimized topography, it can be difficult. Oh, pardon me. It can be very difficult to try and improve the surface finish. So, one of the problems with bad weather in England, you get a cold at this time of year. And so sorry about that. So when we come in to print these intricate geometries like you see on this wonderful illustration here, a lot of those internal surfaces we can't get to polish or to improve. We can't necessarily shot peen and things like that, the normal tricks that we do. So in this case, it becomes really important to see how net section shapes affect fatigue so that we can start to analyze that and build those in to our analytical models.